Howdy, folks. We are about to make a big transition in how we look at the world, all right, and how you look at the world as a physicist, all right. And the big transition deals with the perspective we take on what is an object, all right. And so far, I call this perspective one. Everything that we've said and looked at makes an assumption about what an object is. And that assumption is that, um, you know, objects can move. Sure, we can apply forces to objects, and uh, and but really those forces can make objects move in a path. All right. So objects can move along a path, and what that assumes is that this is an object. And an object, maybe can be pushed like that. And if it's pushed like that, well, maybe that means that the object goes that way. The object definitely accelerates in the direction of that force. Maybe the object was moving this way and slows down because of that force. Or maybe it was moving this way and slows down and then speeds up because of that same force. Groupity group. All right, maybe this object was initially moving sideways, but is pushed down, so it does that and moves like a, or maybe it was shot upward and is pushed down, so it moves like that, right? Or maybe this thing is moving like this, and but this force keeps changing direction and makes this thing move in a circle. That was a poor job of showing that, but the bottom line is that the only thing objects can do is move along paths. And that means that we're assuming something about the object. And that is that the objects are the big assumption we've been making, that objects can be simplified to just be what we call point masses. Now, we're not saying that everything is a point mass, but so far we've treated everything like it is. We've treated everything like the only thing that pushing an object can do is make it move along some sort of path. All right? But that's not what objects really are. All right? And so perspective two, we say, well, what is an object? All right? And the change is we transition from treating everything as a point mass to that objects are extended bodies, and have shape and size. All right, and now what we say is, well, if the object is not just that, but maybe the object looks like this, it looks like a bean, well, you know, and this object has a center of mass that's maybe somewhere cm right there. Well, if we push this object here, something could happen. But if we push the object here, something different could happen. And so where we apply forces to objects now makes a big difference. It has a lot to do with, is this object going to move in a path, or is the application perhaps of a force somewhere like that going to do something else, like make this object do that and rotate. All right, so that's a big transition, and we allow now for forces not just making things move in paths, but forces can make objects rotate. All right, so maybe the force doesn't make something move along a line. Maybe a force just makes something spin. Hang on. So the whole next set of stuff that we talk about deals with rotation, all right? And well, you know, some bookkeeping with rotation and hey, what happens when something's rotating? How much does it rotate? How fast does it rotate? And you know, how much does it turn while it rotates? And then we say, well, why did it rotate? And so we kind of rerun all the stuff we've done so far, treating objects as point masses. But now we say, well, what if the objects aren't point masses, but they have shape? All right, and that leads us to the kind of the where we started our look in physics was at what we call kinematics, just the bookkeeping of what motion is like, and now we look at that from what we call a rotational perspective. All right, so we'll start with this idea, or this. We'll start with this turntable. All right, here's a point on a turntable. That point is right here. That's not really on the turntable, so now it is. There's a point on the turntable, and the turntable is rotating about this axis in the center, and it's rotating, you know, let's say this way at a constant rate. All right. Now, talking about this point, let's define some terms to describe its motion. Well, I'll say during an interval delta t, and time is just the same as it's always been. During some amount of time, what will this object do? Well, you know what? Let's move this object. Let's move the object to here, a little more arbitrarily than saying it's on the edge of this turntable. So this is a solid disk, all right? Well, during some amount of time, this object might move from here, say, to here. And it would move along that path. The object moves along a path while this disk is rotating. Okay? And, well, we've just defined something to be, well, you know what we call that. The length of this line we call S. We call S arc length. And that's a distance. All right? What we're going to be a little more apt to talk about is, you know, that's a distance. We've talked about distance before, but what this object does is, what this disk has done is moved through some angular displacement, delta theta. All right, so over some amount of time, this object experiences, or this disk experiences, some angular displacement. All right, and well, while this whole disk might have a radius capital R, well, the radius of this point's path is little r. All right, so R is radius of circular path. Radius of arc, how about that? All right. Now, here's the thing here. We got a turntable, has an example. Turntable is a radius of 15 centimeters and turns through this angle. What distance does the point travel? So here's the deal. Some of you remember that there's a relationship between S and R and delta theta, and that is that S is R delta theta. And if you don't remember that, well, there you go. Okay, and so, well, let's see. We can say that R is 15 centimeters and delta theta, what we can't really do is use that 140-degree angle, all right? And what we have to do is transition to talking about angles not in degrees, but in radians, all right? And so we got to turn this into radians, and we have to use the idea that a lot of you know a circumference is 2 pi radians. All right, and that's 360 degrees. So that's like or like maybe I just write this as equals 2 pi radians by definition is 360 degrees. All right, and that means there's this kind of magic number called pi, and pi is this ratio of a circumference to a diameter, or yeah, actually that's what it is. So that kind of defines what a radian is, because apparently there's 2 pi of them in a whole circle. All right. So what we have to do in order to use this equation or any of these rotational equations we're going to get familiar with is use angles in radians. All right. So off the bat, we'll say something like 140 degrees. Well, we say there's 2 pi radians in 360 degrees. This is a little factor labeling thing, all right? And you get what you get there. So if we want to get this distance traveled, we'll say S is, well, first of all, we can leave it as 15 centimeters if we want, times our delta theta. And our delta theta, I'm just going to leave as, this is the delta theta, 2 pi radians over 360 degrees. And so, what do we get there? You get that S is, now notice, degrees and degrees go, and well, you get 37 centimeters, but these radians are still sort of there. But we don't write 37 centimeter radians. That's your answer. Your answer is 37 centimeters. Okay? And that sort of leads us to this, a little more about the radian. What's the radian? It's like a non-unit unit. It's not really a unit. By definition, right, we can say that there's a delta theta that we can write. If we say that S is R delta theta, then delta theta is S over R. All right, and so notice that S, an arc length measured in meters, R measured in meters, and so that means that this really doesn't have units, but we say it's a radian. All right, and it's this special ratio, right, where the perfect one is 2 pi. Well, wait, if we want a whole circumference, that's S is 2 pi R. So in a whole circumference, there's 2 pi radians worth of degrees. So the radian is this non-unit unit, this ratio of arc length and radius. Right? It's not a great explanation, but we can certainly talk about angles in degrees, but when we want to relate arc lengths and radii, you have to use your angular displacement or displacements in radians. All right, so a little practice here, right? In 83 degrees, right? Let's see, in a full 360, there's 2 pi radians, and those go, and you get what you get there. Okay, a car tire turns through 275 radians. How many rotations is that? Well, let's see, a rotation. Well, I know that there's 2 pi radians in a full circle, which is 1 rotation. All right. So then you get what you get. I'm doing a little factor labeling here to convert from radians to rotations. And you get what you get. All right, here's a saw blade that spins at 3,000 revolutions per minute. And we want to convert that to radians per second. So 3,000 revolutions per minute. The setup's important. That's how I do them. Now we want radians per second. So revolutions, let's see, in one revolution there are 2 pi radians. And that gets rid of revs and gets me to radians. That's good. Well, and then in 1 minute there are 60 seconds. And then my minutes and minutes go, and I'm left with, and now I have radians per second. Okay, good. And you get what you get. Okay, so this is as bare bones as it gets, factor labeling stuff, converting from one unit to another. You know, you got to be okay with it. 2 pi radians equals 360 degrees equals 1 rotation. You know, you got to be able to use equals 1 revolution. You got to be able to use those things interchangeably. Okay? All right. Now, this turntable rotates. All right, we said this turntable rotates, and we're going to talk about the rate at which it rotates. All right, and really that means the rate at which this is really the rate of angular displacement, or the rate of change of angular position. Well, angular position is theta. Angular displacement is delta theta. So either way we do this, when we say we want the rate of change of either the displacement or the rate of change of the, well, sorry, if we want the rate of displacement or the rate of change of position, we're saying the same thing. What we're saying is that that there's a delta theta per unit time. All right, and we call that omega. I don't think I need this. We call that omega, and this is called angular velocity, which is the rate of angular displacement, or the rate of change of angular position, same thing. All right, again, this is called omega. That's a letter omega, all right, and it's defined to be delta theta per unit time. All right, so here's an example. This ant, the trap jaw ant, can snap its mandibles shut in that amount of time. Are you kidding me? In order to shut the mandibles, rotate through a 90, what's the average angular velocity of each mandible? All right, mandible. So we want average. This is really, I should stress a little that this is average angular velocity, angular speed. All right, so this is delta theta per unit time. All right, now we have a angular displacement. And I don't care if there's 2 of them. I'm talking about one of the mandibles. So one of the mandibles goes from here to there. Snap. And that is 90 degrees. We need that in radians. Lots of you know that's pi over 2 radians. And 1.3 times 10 to the negative 4th seconds. All right, where'd that pi over 2 come from? Well, again, a full circle is 2 pi radians. That means half a circle is pi radians. That means a quarter of a circle, oh yeah, 90 degrees. That's pi over 2 radians. So let's write that radians in there. So what's pi divided by 2? I mean, literally pi divided by 2 divided by 1.3 times 10 to the negative 4th equals, good gosh almighty, an average angular velocity of 1.2 times 10 to the 4th radians per second. Those trap jaw ants. Is there anything they can't do? Okay, fine. Now, what if the rate of rotation changes? What if omega changes? Well, that means that angular velocity changes. Well, and of course that takes some time, right? The rate of rotation changes in some amount of time. Well, we can define how quickly omega changes, or the rate of change of omega, and that means that we do the rate of change of omega, delta omega over t, well, that's what we call alpha. Please don't say fishy thing. Please say alpha. I know I've been using this to mean is proportional to. Now it means, well, now it means rate of change of angular velocity. But that's a mouthful. So we'll call it angular acceleration. Alpha. If it's too hard to remember alpha, instead of saying fish-looking thing, then make a flashcard. Okay, it's not too hard to remember. Okay, so now we have a preview that just speed changes at a constant rate. What's the average angular acceleration? Okay, well, from the last one we had that the average omega was, well, whatever it was, right? 1.2 times 10 to the 4th radians per second, I believe. All right, well, that's the average. Now remember, the average of any two values, especially if there is a the ant's jaws change angular speed at a constant rate. That means that there's one speed, and then I mean we can really do this. There's, well, 1 omega, and actually we know what the initial omega is. Oops. In this case, there's some, right? We say that the assume that the ants jaws are, what's the average angular acceleration? So let's assume that the jaws start at rest and then they get faster at a constant rate, and they get to some omega final. Here's omega naught. Well, the average is this. And how do we find that? Well, we say that's the initial plus the final over 2, right? If you want to average 2 test grades, add them, divide by 2. So what's the average angular acceleration? Well, acceleration, alpha, is delta omega over t. And delta anything is final minus initial. Now we're assuming that omega naught is 0, so let's get rid of that. And that means, well, what's omega final? Well, omega final, it seems like if we say that omega naught is 0, this expression up here tells us that omega is 2 times, final omega is 2 times the average. All right, so this says that alpha is 2 times the average over t. All right, so then the numbers aren't as important. 1.2 times 10 to the 4th radians per second, and I believe that, what was that time? That time was 1.3 times 10 to the negative 4th seconds, and you get what you get. But it's a really big number. It's something 10 to the 8th radians per second, right? Radians per second. Well, that's radians per second squared. A lot like meters per second squared, right? Except that we're talking about angular stuff, so instead of a length of something in meters, we have an angle of something in radians. Okay, so you get, that's, 2.4 divided by 1.3. Let's call that 2. That's like something like 2 times 10 to the 8th radians per second squared. That's a really big number, and it means that these things sure speed up fast. They get faster really fast. I'm sure they do. That's why they're called trapjaw ants. They can close those mandibles in a really small amount of time. Okay? So what you start to notice, maybe you need to start to notice that there are some analogies between linear stuff and rotational stuff. All right. Remember, in linear motion, we defined average velocity to be the rate of change of position. Well, in rotational angular stuff, we say that angular velocity average is change in angular position per unit time, the rate of change of angular position. All right. We said in the linear side that, well, there's average acceleration, that's delta v over t. Well, on the angular side, we now have average angular acceleration is delta omega over time, rate of change of angular velocity. Well, and then there are the other kinematics equations. These are the bare bones ones, group to group. You can do a lot just with those. You can do a lot just with these, but in some situations it might be more convenient to be able to remember in linear stuff use like, well, VF, not VF, but just V final is V initial plus AT. Or sometimes it's convenient to use V final squared is V naught squared plus 2A delta X. Or delta X is V naught T plus 1/2 AT squared. Well, when we do angular / rotational stuff, the analog part of an analogy to this is not final linear speed, but final angular speed. Is initial angular speed plus, well, not linear acceleration, but angular acceleration. And time is just time. There's no linear time and angular time. All right? And this one says, well, it's not linear final velocity squared, but angular. And angular. And not linear acceleration, but angular acceleration. And not change in linear position, but change in angular position. And this one goes omega naught t plus 1/2 alpha t squared. Please be extremely clear about this. That doesn't say A, not A. Alpha, alpha, alpha. Okay, so hopefully it's not a huge stretch to go from, all right, I get it, there are these linear quantities, velocity, acceleration, and displacement, and then there are what I call rotational analogs. There's angular velocity, there's angular acceleration, here's angular displacement. Okay, so this is a new set of, sort of a new set of equations. It's ones that we've used before, just now in a different perspective. Here's a couple of examples. All right, so these are kinematics problems. The bit of a ding, 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 ding. At constant angular acceleration, 2.50 radians per second. Initial angular speed, I thought omega was angular velocity. Well, angular speed, angular velocity, we'll call those the same thing, is 5 radians per second. After 4 seconds, what angle has the bit turned to? Delta theta is what? That's the question. Well, is there an equation that has these 4 things in it? You're darn right there is. It's delta theta is omega naught t plus 1/2 alpha t squared. That means that delta theta is omega naught 5 rads per second times 4 seconds plus 1/2 of 2.5 rads per second squared times 4 seconds. Don't forget the square. Let's see, that's 20 radians plus, let's see, this is 16. Half of that is 8, and 2.58 is another 20 radians. So that means delta theta is 40 radians. How much is 40 radians? Well, it's 40 radians, and if you want to know what that is in degrees, then convert. Oh, that's part A. Part B, after 4 seconds, what's the bit's angular speed? So that's A. B says we want final angular speed. Well, I would say omega naught plus alpha t. That's what I would do. So that's 5 rads per second plus 2.5 rads per second times 4 seconds. And if I'm not mistaken, that's 15 radians per second, right? 2.5 times 4 is 10. 2.5 times 4 is 10. Yep. Yep. 15 radians per second. Okay? All right. Wind turbine spinning through a constant or at a constant angular speed. All right. Initially spinning, and then the wind strength increases and the turbine experiences the constant angular acceleration of that. After, holy cow, 2,870 revolutions, angular speed is now something new. What was the initial angular velocity? Well, let's see. Here's what we have. We have an acceleration of 0.14 radians per second. We have a delta theta of 2,870 revolutions. I mean, boom, right off the bat, I'm turning revolutions into radians by saying that every revolution contains 2 pi radians. And we have an omega final, 137 radians per second. And in part A, we want the initial angular velocity. Question? So, here, an equation that has these 4 things in it, well, that's omega squared is omega naught squared plus 2 alpha delta theta. And we're looking for omega naught. So omega naught squared is omega squared minus 2 alpha delta theta. Or, there's a square rooter to do. All right, if you run that conversion, and then you plug in your numbers, I get omega naught is 117 radians per second. Okay? Okay. Now, it's actually plus or minus, but we're going to take the plus because I'm not assuming that the turbine stopped spinning and then spun in the other direction. I'm just assuming it sped up from one to the other. Okay? All right. Let's shrink that up. Part B is how much time elapses whilst the turbine speeds up. Well, time. Here's what we now have. I would use this omega naught and this omega final and that alpha, and I would say omega is omega naught plus alpha t, and t is omega minus omega naught over alpha. And that delta omega is, like 20 divided by our alpha, 0.14. Yeah, that took 143 seconds. What do you think? Yeah, so this, if you're able to make the leap from one set of equations to another, because we can accept that there are quantities that deal with motion in a straight line or motion along a path, and there are quantities that deal with motion as it.
At this point, block 3 is over.
Motion as it pertains to rotation. Well, if you can accept that, then here's a new set of equations. All right, and again, why? Well, because it really goes back to here. It goes back to the question of what is an object. All right, are objects, sorry about that, are objects really just these point masses that all we can do is push on the object? Or are objects actually physical objects with real shape, and we can push on a different place, and maybe that pushing here makes this object rotate as opposed to move in a line? So we got to be able to account for some more real world stuff where not everything's as simple as maybe sometimes we'd like to say it is. Okay? Okay, see you soon. Send me questions if you have them. Yeah.